Hello community! Today we have some crazy new idea in AI research and we will implement a HyperTree AI system. So let's have a look. You know three of sort, yeah? Each edge connects here a parent node to one, and please note, only one child node. And you're already saying, hey, this is better than a chain of sort, yeah? But you know what? There's something else waiting for you. Because imagine each hyperedge connects here a parent node to a group of child nodes. This would open up complete new possibilities for planning here solution in AI systems. And yeah, this is exactly what we're gonna have a look at. We want to increase the performance of AI system, and we have a look at the planning process. And planning has long been recognized as the core skill for intelligent agents. If you're looking for the intelligence in agents, it is not that it can execute a solution, but it has to find a solution. It has to come up with a plan how to build, how to design, how to construct a solution. And this planning exercise, if it's a complex task, is not easy at all. And you cannot rely on pre-training, supervised fine-tuning here, or on some reinforcement learning methodologies. Planning is a miracle in itself. Now we have tools, no? Told you about in-context learning. My last video was about in-context learning. You know chain of thought, this is a standard, or tree of thought if you're a little bit more advanced here, and you implement this in today's work. And you even have here specialized agent today, you know, this agentic system, no? And they collaborate through structured processes to tackle here this complex planning task. And they want here to extend here the scope and the effectiveness of the planning solution. And again, I really think that this is here the real intelligence of AI. Find new solutions. And you see here publications where different teams here try to find here a better planning methodology. Now, you know, we have current quite some limitation. We have limitation here from in-context learning. They highly depend here on the quality of the provided examples, requiring here significant human expertise and constraining generalization capabilities. And even if you go with autonomous agent methodologies where you have an autonomous agent, you rely so much on its training data on the human-designed intervention, requiring here manual creation of distinct personas and task-specific description for each agent. And if you just modify your task a little bit, your query a little bit, the whole multi-agent autonomous agent construct will collapse. So we have to try out something new, and there's a beautiful new idea of a HyperTree structure that will help us here in our thinking process, a more structured thinking process. Now, if you know a little bit mathematics, a HyperTree is a hypergraph without any cycles. Great. If not, never mind. We address now the challenge of more complex planning tasks within the AI system. So we want to extend the reasoning step here, multi-day travel planning, you know, and you have a lot of restriction from budget, from time, places you want to see, times you want to be at, the amount of leisure time, the amount of travel time, the amount of cost, whatever. And the management of all the different subtasks, and they have to be interwoven, you know. When you book a flight, what city will it lead to? Do you find there some cheap hotels? It is an optimization problem. This is it. You say, hey, I don't want to spend more than, I don't know, $1,000 for the family for a weekend. So find the best solution. We need a little bit of spark of genius, no? You know this. So here now our new solution introduces now the HyperTree structure to model here the planning process. So we have to find from thousands of possible planning processes, we have to find the one that is a real blueprint that will provide us, if we execute this blueprint, the solution. So we are not there yet that we have the solution, but we are looking for the blueprint. Don't make the mistake to mix up here the things. And you know, we don't go for the classical tree of sort. It's now 3 years old, which uses here binary split, but we will go for the new HyperTree, where we will build hyperedges, and those hyperedges connect multiple child nodes. And this will be crucial. We will have a decomposition to break a specific task down into nested subtasks. So we will not have completely independent subtasks, but all are interlinked. Think about the example that I showed you. Book a cheap flight. So maybe you go from London to San Francisco, or you go from London to New York. And then you have to think, hey, I need a hotel for the family. So where can I find a cheaper hotel in San Francisco or in New York? And what are the sites my family wants to see? So you have quite some constraint and you want to bring all into the optimization problem. And you do not want to solve it sequential, like in a tree of thought. So multi-path exploration is here the term that we are looking for, simultaneously evaluating different strategies, different transportation options, different budget constraints. So just to make sure, because I made a mistake and I thought, hey, this is just a tree of thought with more child nodes, no? It's not. It is definitely not. We go, if you want here, if you think about dimensional spaces, we go from a flat branching out in a tree of thought to a more structured decomposition. So by grouping now the subtask into our hyperedges, we enable the LLM now to think in layers. We don't think here just in one-dimensional objects, you know? I have one edge that connects one node to one other node, and then I have one other node that connects to the next other node. No, I can think now in higher complexity spaces. Think in layers. Explore strategies and not just isolated options from one to one. Manage more complex constraints in the complete system in parallel. You know here the mathematical definition for a tree of thought explanation, if given here the state, how the LLM generates then multiple steps, each of which remains independent in its subsequent expansion. Therefore, this is, if you want here, in the definition of the tree of thought, is here the objective that we want to overcome because we want to achieve a better result in the reasoning. So therefore, give you here the definition of a hypertree, but this is a rather dry mathematical definition. If you love it, here it is, great. But you know what? For the rest of the video, I just have one goal. I want that you really understand what is a hypertree. Because if you miss out on this one, the whole new methodology, the whole new publication, the whole new code is for nothing. You have to understand that there is something new happening. The spaces of the node, around the nodes in a graph image, in a graph visualization, explode now. The spaces become so much bigger. Let's have a look. In a classical graph theory, you know you have two nodes and you have one edge, and an edge connects two nodes. You know this classical graph theory. Now, in a hyperedge idea, you can connect any number of nodes simultaneously, not just two. So a single hyperedge can link a set of nodes. I've chosen here a particular configuration of 1, 4, and now you imagine this is not that you have here an edge here, an edge here, an edge here, and an edge here. This is just one edge. Imagine like Schrödinger's cat, you know, quantum mechanics, no? This here is connecting all the nodes, this set of nodes, and it is only one edge. Yeah, it is a little bit difficult to understand because we have never seen this in real time, but we are talking about mathematics, we are talking about higher dimensional spaces, we are talking about a little bit of set theory, of functor theory, a little bit of function theory. So we need this a little bit different mathematic here to go the next step in the complexity and find better solution. Yeah, you know, a standard graph, if you know graph theory, is just a special hypergraph where the hyperedges happen to link exactly two nodes. So you see everything converges here, everything falls back here to the simplest possible solution. You see, it's not that complicated. Another example. A cake recipe. You can think a cake recipe connects here 4 ingredients, flour, sugar, eggs, and butter, and is therefore an example of a hyperedge. Because the cake recipe hyperedge links all of those ingredients needed for that specific outcome. If you want to bake a cake, those are the ingredients, maybe a little bit of water, that you need to have. So you don't have a link at first the flour and then another edge to the sugar, and from the sugar another edge to the X, and then we have another edge to the butter. No, this is all here one hyperedge. Yeah, HyperTrees or hypergraph without cycles, I told you this. Now, the standard tree in the graph theory is just a special kind, because it has roots, parents, and children, and there's just one rule if to remember. And when a parent node has children, each child is typically connected by one separate edge. This is it. This is the standard tree. And now we break with this. So, what is here the core new idea? Again, compared to the, if you want, tree of sort, the LLM outputs M distinct alternative sentences or alternative actions. And each sentence or each action becomes a new separate child node. This is the way the tree of sort works. But we go a step further in the complexity. We saw the LLM, guided now by a rule that we have to specify, outputs now a set of related subtasks. Notice related. So this entire set is what the parent node decomposes into via now this new one hyperedge. So while both explore here a space, if you want, the tree of sort explore a space of alternative sequential steps, while our HTP explores here a space of a decomposition into sets of concurrent subcomponents. If you know mathematics a little bit more, you have an idea what's happening now. Now, the generation of the next step, easy. No? Tree of sort, again, that you see exactly the difference, leads to M separate child node, each representing one of those alternatives, and their independent lines of sort being pursued in parallel or sequentially explored in the TOT. Now, in the HTP, we have a single hyperedge connecting X to that set of subtasks. The subtasks are now the new nodes to be considered within that branch. And yes, they are interdependent. And now we can apply the mathematics on this structure. Here is the beautiful study, highly recommended, May 5th, 2025, HyperTree Planning, Enhancing LLM Reasoning via a Hierarchical Thinking Process, the University of Science and Technology in China, Huawei Technologies, and the College of Intelligence and Computing, Tianjin University. Great idea, beautiful paper. Have a look at it in detail. They have a lot of data, but I just want to communicate what is really the main idea, the HyperTree planning. What is HTP? Now let's have a look at this single decomposition act. This is the simplest form if you want. So you have a parent node in HTP and you expand it now using a rule and it creates here now a single hyperedge. And this hyperedge now connects here the parent node to a set of the child nodes. But remember, the child nodes are not alternative paths from the parent in the same way. Instead, they are constituent subtasks that the parent task has been broken into. If you, maybe this image helps you better, né? You take a huge node and you break it into different subtasks, and you have only one hyperedge that connects here to the set of child nodes. Interdependence by the definition of the parent task, the child node created by a single hyperedge expansion in HTP are interdependent in the same sense that they collectively represent the full decomposition of the parent task according to that specific rule. And here I've given you a very simple example. If you have to plan a trip and you have a hyperedge that consists now of a set of arrange the flights, book the hotels, and plan the activity subtasks. But of course, you do not only have broken nodes and exploding spaces around those broken nodes to give you here an end set of alternatives, but you have real alternative choices here within HTP. So if, let's say, the book hotel here could be decomposed by a specific rule in a sub-task, and let's call them A and B, there would then be real alternative ways. Now you have to decide to handle here how to book the hotels. So here you really have now brought back the alternative into the decision making, which planning blueprint here to generate. Great. Yeah, I think more or less just let's look here at the benchmark data. They give us here for 2 systems for GPT-4 Omni and Gemini 1.5 Pro, so really the old system here. You have here all the different models here, chain of sort and the tree of sorts. Then here all the different agent solution, plus here with HTP here, their system. And you see here in bold that they have here real good performance across different benchmark. If you want, you find all the details in the study. Really interesting. But let me go one step further. You remember hyperchain? A hyperchain is now a path through the hypertree. And if there are multiple ways to decompose here the nodes at various levels, you'd get here multiple possible hyperchains in your hypertree. These hyperchains could be seen as something analog to independent branches of your tree of sort, as now they represent different complete outlines. But if you want, you can also go here to Markov decision processes. If you want to have this perspective on the system, you can say, you know, this is really similar here to a Monte Carlo tree search. Remember, Monte Carlo tree search, you go through the tree and you find here, then given a specific time budget or a computation budget or whatever limitations you have, you find a final solution. You backprop here the system through the complete tree. Now, TOT branches, you know, independent alternative reasoning path, don't have to talk about this. But our HTTP child set from one hyperedge are co-occurring subtasks that are components, interdependent, and the overall path now in the hypertree, the hyperchains in total. If multiple decomposition choices exist at the various points, different hyperchains can be formed in these complete hyperchains and then evaluated. But remember, they are not evaluated now like a Monte Carlo tree search with a reward function that we have in RL. But now we have a different system. We have the LLM itself choosing here the right blueprint that it thinks, given its pre-training and supervised fine-tuning and reinforcement learning, which of those blueprints to select and explore independently before one is chosen. The algorithm here for the top-down hypertree construction algorithm is rather interesting, but now we have all the elements to understand immediately how to build this. It is not the simplest, but it is raw if you have understood the theory behind it. And this is why I was so repeating. Now it's rather easy. Yeah? You have a pre-processing the rules. Then you have the construction process start with a very simple hypertree that contains, of course, only the root node at the beginning and the initial query. And then we have here the different flattening out into distance C1 to Cm. We can filter now the hypertrains if we have too much, if you have restriction on this. Beautiful. You can prune them. There are 3 different methodologies to prune the hyperchains you will find. Then you will expand the node here. If you want, this is here what I think is the core step here. You have here the policy takes the original query, the current hyperchain CI, the node to expand G star and the specific rule, and generates here a set of child nodes. And this set represents here the subtask that G star decomposes into when the rule is applied, and this set forms here a new branch in the hypertree. And then you have the attached node function that updates here the main hypertree. So it takes here the newly generated set of child nodes. We form here a single hyperedge branch and attaches it as child to the node G star within the context of the hyperchain CI that was processed. And now we come to the final one. And from all of those hyperchains, now the LLM itself decides here or selects here the optimal hyperchain. So you see, no reward function up until this point. But the LLM says, hey, I think given my training data, this could be it. And here you have now the famous last words, the conclusion here by the authors. They introduce HTTP, a novel planning paradigm that utilizes here the hypertree construction for a structured hierarchical thinking process. They're iteratively expanding here the hypertree through a top-down process. HTTP enables here a multi-level divide and conquer strategy to create an effective planning outline. And they evaluated this, and I've shown you here the data. HTTP consistently outperforms the older model they tested. And this is great. And they think this is a real new highlight in the effectiveness in tackling complex AI planning challenges. And up until now, you remember it was only done more or less here if we have now an outlook here on the, if you want, mathematical dimensions here of optimization. But this would open up the way away now from pure mathematical, logical, formal reasoning structures into a more human reasoning pattern. Yeah? So no direct numeric backpropagation here of a terminal reward system like we have here with Monte Carlo tree search and reinforcement learning. The hyperchain selected by the LLM final judgment as an optimal outline, and we have only implicit qualitative signals. So this is like asking an expert to look at several draft blueprints and pick the most sensible one. So this is not really what we might be happy with in the long term, because this depends a lot of the training data, the experience of the LLM, the fine-tuning and the reinforcement learning of the LLM, to what particular domain have solution been produced, where has the fine-tuning, this task-specific downstream task focus been applied on. So therefore, you are a little bit careful that this is not an LLM specific solution. But if you want to learn more, I have multiple videos here on Monte Carlo tree search for ICLM smaller language model, or if you prefer here in the Tomorrow Machine here, Monte Carlo tree search explained in detail on an AI strategy structure, or if you want just to see here from Stanford and UC Berkeley Monte Carlo tree search enhanced AI agents, this is the video for you. And of course, if you want to go here from a training time here to the test time training adaptation, I have this video on novel policy reward structure with Monte Carlo tree search. So really the step before the HyperTree of today. So there are a lot of information waiting for you. But I think what's really interesting, the next step here, you remember Monte Carlo tree search is designed for problems where you can find a clear terminal state, the end state, and a numerical reward that you have to define in games, mathematics. And the reward signal, remember in reinforcement learning here, is kind of a bedrock here for the search optimization in the search space. And now if we let here the spaces around those nodes explode in complexity and in dimension, now if we have more complex planning capacity by our methodology and our AI system and our vision language model, and we use here HTTP, then often doesn't have a simple numerical reward function for intermediate plan structures, but we have to take care about the linguistic complexities too. So we can clearly see what would be the next step here. We could go from a Monte Carlo tree search here for a Monte Carlo HyperTree search. I think this will be absolutely fascinating. I'm looking forward to the next publication from this particular research team, because I think this is the logical next step that we go here in the complexity, the next level up, and then we have HTTP as a real powerful new methodology. I hope you enjoyed this video, and if you want to see more, hey, why not subscribe? And I see you in my next video.